Hey guys, welcome back to the series of videos on STA. In this video, we will try to understand the basics of delay calculation reports of timing arcs. That is basically the report delay calculation is what we are trying to understand. So guys, I assume that you guys are aware of what are timing arcs and types of timing arcs, etc. If you are not aware of it, I would like you to go through my previous video on basics of timing arcs. I will keep the link in the description box. So let's get started. We will look at both cell delay arc and net delay arc in this video because there will be slight differences between the cell delay arc report and the net delay arc report. So to get the delay calculation report, we can use the command report delay calculation. In this case, I have reported a cell delay arc, which is from the input of this instance 2365 to the output of this instance 2365. All right, this is what the report we will get if we execute this in prime time. So we will try to understand what are the components of this, right? To do the delay calculation, the engine needs the input transition. That's why you see this input transition is mentioned over here, and it also needs the output load, right? Based on that, it will obtain the cell delay. Instance to the 65 output pin is used here, and it is mentioning that this is the RC network on the output pin that it is observing. So finally, with this and this input transition, it will obtain the cell delay, which is reported here. We will go from the top to the bottom. So what are the information provided here? It is mentioning from pin, it is mentioning the to pin, and it also mentions the library units, and it also mentions the library, which particular corner library it is, and again mentioning the library units and the library cell, which particular cell this delay is corresponding to. So that's also mentioned here, right? And it also mentions the arc sense of this logic cell, right? So what is the meaning of arc sense? It's basically the uniqueness of the instance. So what is the meaning of uniqueness? For example, positive unit it is mentioning. It could be a negative unit or it's a non-unit. It depends, right? So positive unit means if there is a signal which is rising at the driver, it will be rising at the receiver. If it is a negative unit, if it is rising at the driver, it will be falling at the receiver. So arc type is basically cell type here. So arc type could also be the net. Then it mentions about the RC network on the output pin. So this is basically our load, right, is what we are looking at. So the output pin of this instance has these many capacitances and these many resistances, and it will combine them and it will provide you the total capacitance it is seeing with, all right. And total resistance is also mentioned, which is 1.65 kilo ohm. And then we will see these parts, all right. This is basically the input transition, the effective capacitance. The effective capacitance is different from the total capacitance, as you can see, right? The output transition time is basically the 10 ps, and here if you see the input transition is 57 ps. So it has significantly boosted the signal to reduce the transition time. So also it is mentioning that the annotated max delta transition basically 0. So it's telling that there is no crosstalk at the output pin, right? And also it's showing that the pin transition over here, which is the output pin transition. So it's also mentioning something very important here, which is it is saying that the advanced driver model used for rise and fall, and similarly advanced receiver model is used for rise and fall. All right, here it's saying that it is CCSN, and here it's saying C1CN. What are these things? To do the stage delay calculation, it does more accurately and efficiently using models. It will treat the driver and the receiver as models, right? So these models represent driver, RC network, and the capacitive load. So this is the driver, this is the RC network, and the capacitive loads will be here. There are multiple models such as NLDM, CCS, and other models, so that we can accurately estimate the delay. All right. So there is a app variable which is called RC driver model mode, which can be used to make changes with respect to which type of model we want to use. So the options are basically basic and advanced. If by default it will be advanced, so this is what it is telling over here. Basic means that NLDM model will be used, nonlinear delay model, and advanced mode means CCS, which is composite current source model. So in this case, CCSN means composite current source noise model, which will use its own spice related data in it. And C1CN is basically the receiver model of the CCSN itself. So it's basically multi-segment receiver capacitance model, which is used to determine the capacitance of the receiver cell. All right, so these are the details that it will mention. So in case if it is using NLDM, you should know that it is not so accurate that the delay is what we are getting. For PNR level STA, NLDM model is highly used because it will save a lot of runtime and memory. But for sign off, it's a must that we use CCS or CCSN models. Next, we will go for the net delay arc. Since there are very few changes between cell delay arc and the net delay arc reports, I will focus only on the differences between the net delay and cell delay arcs. So the first two obvious differences are this arc sense and arc type. Basically, the net doesn't usually change the logic of the signal or sense of the signal, and the arc type is basically net. In this case, the other case was cell, right? And the other changes are basically at the beginning it is mentioning the overall delta delay, and here it's mentioning the delta transition, and there is a change called arc delay, which was not mentioned before, because this arc delay in this net arc is basically the sum of the net delay and also the delta delay, right? So if you check 23 plus 5, it would almost become 28. Similarly for the fall. So other changes are like you can see that the from pin is being used, and that's where the RC is calculated, because since it's a net arc, you will have RC values calculated from the beginning of the from pin, right? And another difference is that it is showing you clearly that there are two capacitances in receiver model, and that's also advanced receiver model. In this case, it is also C1CN model, basically exactly the C1C2 model, because there are two capacitances which the tool will dynamically change depending on the situation and gets the accurate capacitance value. That model we will discuss in further videos. All right, and also you have the net slew degradation. This is one very important thing that you would see, right? Like if you see that the input from pin transition time was 44 ps and 2-pin transition was increased to 57 ps. So the slew has been degraded about 13 ps from the input to the output. I mean the from pin to the 2-pin, right? So this much is the degradation in the slew. These are the information that you can use to analyze any timing arc in any critical timing paths. So that's all in this video. Thanks a lot for watching. I'll see you in the next video. Bye bye.